In this video, we are going to talk about singular value decomposition and principal component analysis. These are two of the most important concepts these days in machine learning and data science. It's also very important for us to understand as in terms of numerical linear algebra. So what are the applications of what we call singular value decomposition, or SVD? So one application is what's called the dimensionality reduction. In other words, if you think about a data set with D features, let's suppose you collect the data set and you have D columns. Each of those things refer to one feature. And D features could be thousands of features, for example. And you want to reduce them to just a few features, let's say P, number P, which is going to be somewhat smaller than D. Another application would be more like image feature extraction, which is the same idea. It's the dimensionality reduction. So the idea would be approximation to the image with less memory. Essentially, if you think about an image, it's a set of pixels. And within those pixels are the patterns or shapes that make up the image. So you want to take those pixels and think of each pixel as a feature and then reduce it to a few of them. And it's more like a compression kind of algorithm. The other application is in what's called the document corpus analysis. You have a corpus of documents, you have a set of words, matrices of words and frequencies. So you have words on the row, the columns are the documents, or vice versa. It doesn't matter. The frequencies are the numbers on that table. So it is a matrix. And you have these documents with words and frequencies, and you want to extract some characteristics of these documents. Maybe there are 3 or 4 hidden themes inside those documents. And you can do that by doing this corpus analysis. The other application of SVD is the recommender systems. So you have a lot of recommender systems. For example, on Amazon or Netflix, you get recommended things based on what others may like. Again, those are generated from user item matrices, and then by extracting the features to reduce them to a set of small features. So we'll talk more about that. So here's these two tables shows us, for example, here's a matrix with the columns to be the movies, and the rows are the users. So you have user 1, user 2, and so on. And each user rate the movies. And as you can see, there's a set of ratings here. So it seems like the first set of users are rating more those first 3 movies. And then the second set of users are rating those. The same thing we'll talk more about those things. So the idea is to take that matrix and break it into a format like this. The other idea, as we talked about, that in the document corpus analysis, you have a bunch of documents, and then you have words. And these are the docs and words. And then you got some matrix, and you want to kind of see which categories. So for example, you might say there's a bunch of documents that are related to terrorism, and the other documents related to entertainment. Okay, so what is singular value decomposition? The idea is that given a matrix X, we can factorize that matrix into 3 matrices, U, S, V transpose. So this matrix X can be any dimension. It doesn't have to be rectangular. So that's the nice thing about these things. because you don't have to have a rectangular matrix. And in this case, the S is a diagonal matrix with some non-negative numbers on the diagonal, which we call singular values. And U and V are orthogonal matrices. Essentially, they have this property that the U transpose is the inverse of the matrix. In other words, all the columns of U are orthogonal to each other. This can be obtained by a Gram-Schmidt process, that sort of thing. We have seen those things. The matrix S contains the eigenvalues of X transpose X, which we will call it a covariance matrix. We'll talk about that. And they are called the singular values. In fact, these are the square roots of the eigenvalues of X transpose X. So the way you think about singular value decomposition is, given an m by n matrix, you're going to get this long matrix, which is m by n. That matrix is called U. And then you're going to get a matrix S, which is that contains the singular values Sk along the diagonal, and which is a square matrix n by n. And then you get the V matrix, which is usually a wide matrix. In fact, in this case, it is n by n. So it's a square matrix in this case. So you get a bunch of a matrix which is a square matrix. So that's the main idea here. So to write X as U S V transpose. And surprisingly, this decomposition gives us a lot of things that we can do, we can think about. Okay, so what is an interpretation of this singular value decomposition? So let's say that you have a matrix A, which is a user item rating matrix. So users on the rows, each user will rate the items. So you have items as columns, users as rows. You might imagine when you buy something from Amazon, you might rate that, you might not, most people don't. That's why these matrices are typically very, what we call sparse, because most people don't rate all the items. There are thousands and thousands or millions of items in Amazon, and there are millions of users in Amazon. So you can think of this as a very sparse million by million matrix or something like that. It's very, very large. Now, when we take the A and do the singular value decomposition, let's say do it like UDV transpose, where B is the diagonal matrix with what we call singular values. And in this case, the U is more like a user category matrix. So you can think of, right now, what we see from the matrix is the user item matrix. But hidden among these things is a category. So you might see certain users like certain categories, but it's not very clear from the matrix itself. You got to do some analysis to see that. So think of U as a user category matrix. Again, these categories are not identified, they are latent. So we have to figure out what those categories are. Categories. Okay, so this is then the V is an item category matrix. So you have user category and item category. So users like certain categories, items are in certain categories. And D is the strength of each of the categories. So you can think like this, what is the strength of this data set for each of the categories? So one example, one other application of singular value decomposition is what we call, we can image feature extraction. For example, we can start with a an image which is 200 by 300. So we have an image which is 200 by 300. So that you can think of this as a 200 by 300 matrix. Now in this image, if you look at this image, you can think of each pixel as a feature. So there are many features in this image. But hidden among those features are the hidden. So there are many features, but we want to find the most important features. For example, we want to see the shape of the hair, or shape of the shirt, or the face, and so on. So what this example is showing you is that by taking the singular value decomposition of this matrix A, which is say 200 by 300, we can slowly recover the features within this image. As you recover the features, the image becomes more and more clear. We'll talk more about that. So that's one of the interesting applications of using singular value decomposition to find the hidden features of an image gradually. An application, this could be as an extra, we can say, so for example, if you think about the original image, that would require 200 by 300 pixels to store, but you could get a rank 1 approximation by a much smaller set of bytes. And that can be very important for data transmission and other kinds of situations. Okay, so how do we do that? So the image feature extraction is, so we think about an image as a set of a matrix of pixels, and each pixel has an RGB value. So usually this is 1 byte. All pixels they have a number value between 0 and 255. So we take these R and G and B matrices, and we apply the SVD to each matrix, RGB. So for each matrix, you're going to get a singular value decomposition. And if you assume that UI and VI are the columns of U and V, then we can approximate a matrix by taking this U1, so this is U1, and V1 transpose. This is V1 transpose. It's a column matrix and a row matrix. So this is the largest singular value. Singular values are ordered from largest to smallest. S1 is the largest. S2 is the next largest, and so on. So if you take one column of U and one column of V and multiply it, you're going to get a matrix, and then multiplied by the intensity, which is the singular value, you get an approximation. If you add another singular value and the second two columns, so you say you have U2 and V2 transpose, now it's a better approximation because you added a few more another term into this. So the more terms you add, the more clearer the image will get. And if you add all the terms up to the kth term, then this summation on the right is exactly equal to the image itself, subject to round-off errors and other things. But it's pretty much the same thing once you get to once you add all the terms. So one example of this, one application of this idea is that we could just think about how to reduce the size of an image by removing the unnecessary things, or the features that might not have any much significance, which are exposed by the singular value decomposition. So again, the basic idea is that given a matrix A, you find a decomposition, then you can write the A as a sum of these terms, where U1 is the column 1 of U, and V1 is the column 1 of V. And singular values are ranked from highest to the lowest. When we say a rank K approximation, what we do is we take the first K terms of this equation 1. So you can do rank 1. Rank 2 means you get two sets, two terms, and so on. Okay. And we will also note that the singular values are the square root of the eigenvalues of A transpose, which is we call the covariance matrix. So here's an example of a singular value decomposition. For example, let's suppose that you're given this user movie matrix. So you're given this user movie matrix, and the movies are Matrix, Alien, and so on. And the users, all users, rank the movies. So in this case, users 1, 2, 3, 4, 5, 6, 7, whatever, and they rank the movies. And from this picture, it's kind of clear that there's a group of users here who like the same kind of, probably that might define a category. Here's another group of users that might define another category. Although it shows up very nicely in this matrix, which you can see sort of a block format, these columns and rows can be all mixed up. So it might not be trivial to see this kind of grouping. But if you do the USV transpose, which is the singular value decomposition, you might get matrices where you would say that the hidden among this rating matrix are the concepts. Maybe the first 3 movies are the science fiction, and the next movies are the romance. And there's a category that's not very clear what it is. It could be mixed in it, but it doesn't have much of a weight. If you look at the weight for that category, the third column would be about 1.3, which is not good. Okay, so the highest weights are given to the first 2 singular values, 12.4 and 9.5. So essentially, if you create a rank 1 approximation, you would take 12.4 times the first column of U, which is like that, 0.07, and then you take the first row of V. So we take 0.56 to 0.09, and that's a rank 1 matrix. Now, if you want to create the next term, you can take 9.5 and take a column of U and a column of V. So that would be the second column, 0.02 from this one here. And so you take that column, and then you take this row here. So that would be 0.12. This row here, right? And so you get that, and then you also get 1.3 times something and something. If you add these 3 terms, you should get the matrix exactly as is. But what we can do is we can just drop this one. We don't really think that's very significant. There are only 2 sort of hidden features here, which is given by the singular values, 12.4 and 9.5. Now, you can easily find the SVD, or singular value decomposition, using MATLAB. Just enter the matrix and type SVD of A. You can get the singular value decomposition, the U, S, and V. So notice that here the singular values are 12, 9, 1.3, and so on. So these are the singular values for the matrix we saw here. And notice that in MATLAB, it gives you a larger number of things. It gives you the 0 singular values as well, but we did not write them in this matrix here. Okay, so the next of what I want to do is to really briefly talk about a related concept called principal component analysis. The goal in the principal component analysis is convert a set of observations, possibly correlated variables, into a set of linearly uncorrelated variables. Essentially, we will take a look at some bunch of variables x1 through xn and try to find some kind of an orthogonal mapping into perhaps a smaller set of vectors v1 through vn. That process is called the principal component analysis. All right, so the way you want to think about this is the following. Let's suppose you're given, let's take a two-dimensional case where you're given a set of points. You plot the set of points. Now, those points are plotted with respect to the original axis x and y. These are two-dimensional points given by x1, y1, x2, y2, and so on, xn, yn. But you might want to ask the question, what if I want to rotate and use a different basis to map these points into? So if I take another thing here, then you might say, okay, if I map it into that, the variance, if you map these points into this axis, excuse me, you can see the points are mapping onto those, and they map on this side to them, these axes here. So essentially, we can take the points and map them into two different axes that are, again, orthogonal. And you have, on this side, you have a larger variance. So variance is preserved. So the question here is that if you have a set of two-dimensional points, and if I want to find an axis where I can map all of them into one, I find some axis, and I say, okay, let's take all these points into that axis. So now suddenly the 2D points become 1D representations. So this is called the dimension reduction. That's the key idea in principal component analysis. So an example of dimensionality reduction is same as SVD kind of thing. Let's say that you have a bunch of housing data, and so you have square footage of the house, number of rooms, number of bathrooms, the school district where the house is located, crime rate, and shopping. So you might imagine that all this is given as, let's say this is feature 1, F1, F2, F3, F4, F5, F6. So they might be given from a matrix, F2, F3, F4, F5, F6. And then they're given for various houses, house 1, house 2, house 3, and so on. So you get a bunch of observations. This is a matrix. But among these things, if you really look into this, you might discover by doing analysis that this actually represents some sort of a size concept, size category, and these things represent some sort of a location category. So from a more abstract way, you can say size is really, so you can think like size could be any of these things, square footage and the rooms and the bathrooms. And then if you take the location, you might have other things. So the basic idea is then, so like school districts and all that stuff, right? So the basic idea is that you go from more specific set of features to more general set of features. That's called dimension reduction, because you might not be interested in all very specific features, but let's go to more a set of general features. That's the idea of principal component analysis. So from a simplified perspective, there's another way to think about this. Let's say that we have a bunch of features. So let's say F1, F2, F3, F4, F5. And then you have observations. Okay, so let's say this is point 1, point 2, point 3, and so on. So you might imagine that we have plotted these points in what's called a 5-dimensional plot. You cannot really do it, but let's assume that we could plot these points in a 5-dimensional. So the dimensions are the features, which is F1 through F5. So we have plotted those points, and essentially you have a matrix. And if you take the covariance matrix, so if you call this matrix X, and X is, let's say this has, I don't know, 200 rows by, let's assume that X is by 200 by 5. And if you take X transpose X, X transpose is 5 by 200, and X is 200 by 5. And so X transpose X is a 5 by 5 matrix. And that matrix is called the covariance matrix. So this is called the covariance matrix. So in other words, it shows you the covariance between, this is the covariance, the idea, this is the covariance of F1 and F1, F1 and F2, F1 and F3, and so on. So those things show you it's a 5 by 5 matrix, shows you the covariance. So then you find the eigenvalues and eigenvectors. So you might get lambda 1 v1, lambda 2 v2, lambda 3 v3, lambda 4 v4, and lambda 5 v5. So you got 5 eigenvalues, and so these are the low eigenvalues, and these are the high eigenvalues. So let's order them like that. And then let's choose maybe 2 of them, because these 2 are much higher. The eigenvalues are much higher, so they have much bigger weight than the other ones. So by choosing 2, you actually reduce your data set to now 200 by 2. So we only have now, first we had features, now we have categories. And there are, say, 200 observations like before, but they belong to certain categories. Okay, so we have that. And now if you plot these points, now we are plotting those points in a 2D plane. So now it's a 2-dimensional plane, not 5-dimensional place. So what we did was we did reduce from 5D to 2D, and that's called the dimension reduction. Now, from a matrix perspective, let's take a look at, oops, yeah. All right, so the final slide in this video is that how do we really, we have a geometric interpretation of SVD and PCA, principal component, and how do we figure this out from a variety of things. Now, there are a few things that are quite important. We say the projections of data on the principal axis are called the principal components. And if you have the matrix factorization, where you have, so given, let's start with the SVD. So if you have a matrix X, I can factorize this into UDV transpose, singular value decomposition. And then if I take the covariance matrix, X transpose X, divide by N is the dimension. And what you get is, you can actually notice that the X transpose is VD U transpose, and X is UDV transpose, because these are orthogonal, that would be I. So you end up with D squared over N, V D squared over N transpose. Now notice that C is a symmetric matrix, X transpose X. And the singular vectors V, what we get here, this is we get vectors here, are the principal directions and singular values and eigenvalues of covariance matrix. They are related by taking the principal components, can be taken by multiplying X by V. Those are the principal components that you want for your analysis. So this is just a quick video on principal component analysis, and singular value decomposition. Hope you enjoyed it.